Hey everyone, I'm JVacek, and today we're going to be talking about a radio transmission system. Unfortunately, due to some technical difficulties with the screen behind me, I'm just going to have to hold the computer, but that's okay. So basically today, we're going to divide this up. We have an amp stage, then we have a mixer stage, then we have a power amp, a bandpass filter, and essentially an antenna. So we're going to take each stage individually and just talk about each one from each class perspective. Oh yeah. I'm in 312, 342, and 332. So let's start with the 312 perspective of a amplitude modulation. So amplitude modulation is very simple mathematically. It's essentially you take your input signal x of t and multiply it by some sinusoidal signal, as we can see right here. So x of t is just equal to x of t times cosine omega naught t. And what we do is, since our voice is only at roughly 20 kilohertz, and we can't actually transmit that signal, it's way too low of a frequency, and I'll get into that later. So we multiply it by some cosine omega naught at roughly, in our example, it was 900 megahertz. So what we can see is here we have kind of just a arbitrary baseband signal, which is our voice, with this spectrum. And we have a cosine omega naught t. And the spectrum of cosine omega naught t is just two deltas. So when you convolve our analog signal with our local oscillator, you get two shifted versions of our baseband signal shifted by omega naught. And our omega naught is 900 megahertz. So this allows us to transport the signal at 900 megahertz, and our signal is essentially encoded within that cosine. All right, so we have three reasons that we do modulation. One is for antenna size, which I'll get into later. Second is frequency mixing, and the third is channel constraints. All right, so does the shape of the carrier signal actually matter? No, it really doesn't. All that matters is that our carrier signal is periodic. And it could be anything, because what a periodic signal means is that A, it has a Fourier series representation, and if it has a Fourier series representation, we can, in its spectrum domain, it'll just be deltas. All right, so now let's move on to the preamp stage. So there's three things we do in the preamp stage. We amplify the signal, meaning we mess with the gain of the signal. The second thing we do is we need to condition the signal, and what that means is we just need to make sure the signal fits the parameters of the next stage. So if we have a preamp, we need to condition it to make sure it meets the parameters of the local oscillator, which it will be fed into next. Third thing we do is filter the signal. Usually our signal accumulates noise as it moves through each stage, so we need to filter out the noise. All right, so how a local oscillator actually works on a circuitry level is we can build a simple one as an LC circuit. Ideally, an LC circuit has an omega naught, aka our resonant frequency, at 1 over square root LC, and it'll create something like this. But there's no such thing as an ideal LC filter or a local oscillator. So what we actually do is there's some attenuation, as we can see right here. And this attenuation essentially causes the signal to go to zero after a while. So what we have to do is we essentially have this transistor tank that fills this quote-unquote LC tank every time it starts to run low. But the purpose of this LC filter, or I don't know why I call it an LC filter, but this local oscillator, is we can get our omega naught from the previous slide at 900 megahertz, which we so choose. And now, how do we actually determine our omega naught? How can we actually change it? Because in cell phones, it's actually programmable to the frequency we want to send the signal out. So what we can do is we have an inductor and a certain amount of capacitors in parallel with transistors, and we can essentially turn on as many capacitors as we need to essentially raise the capacitance and manipulate our omega naught. All right, so now we move to the power amp and bandpass filter. So there's a derivation, but we determine that our current through the drain of the transistor is equal to Vn baseband times our G of T. And our baseband is actually V of S. But the interesting thing about about G of t, it's actually a function of our local oscillator. So all that's saying is our output is a function of A, our local oscillator, and B, our baseband signal, which is our analog voice signal. So what's that saying is that this is essentially amplitude modulation again. Now what we also have here is another RLC filter. And what this does once again is it resonates. It has a certain resonant frequency. What that means, it's essentially the bandpass filter of our system. It resonates at a certain frequency and essentially shorts out all other frequencies. So the only signal we have is our carrier signal times our baseband signal at the frequency we want to transmit it at. And the other interesting thing about this is when we achieve our resonant frequency 1 over root LC, it actually causes the impedance of this to go to infinity, which essentially raises our gain by infinity, which is not theoretically possible, but that's the idea. This is also essentially a representation of our power amp stage with our bandpass filter. So we're getting the signal at this point ready for transmission. Now antennas. Like I said earlier, there's a correspondence between wavelength and antenna size. So if you have a really long wavelength, you're going to need a very large antenna size. So our voice is in the kilohertz range, but what that corresponds to is a wavelength or an antenna size of over 100 kilometers, which is just completely impractical. So what we do is that's why we actually do the amplitude modulation, so we can raise the frequency and essentially make our antenna size much shorter, something in the millimeter range, which is very useful because you can't have a 100-kilometer antenna in your cell phone, obviously. All right, last thing we need to do is, now there's this thing called skin depth, and skin depth is just basically the depth at which an electromagnetic wave has entered a surface and been attenuated by 1 over E, which is 36.8%. And one last thing I'd like to talk about is kind of like the rainy day versus sunny day scenario. So in rainy days, there's a sigma, which is your conductivity not equal to 0. And basically what that means is when your conductivity is not equal to 0, you're going to have an attenuation of the signal, meaning it will die out over time. In sunny days, there will be conductivity equal to 0, which will cause no attenuation of the signal, which is ideally what you want. That's why with AM radio, you're going to have a fuzzy signal when it's a rainy day. All right, that's all I want to talk about. Thank you very much for your time.